Hello everyone, welcome back to another video of Math 215. In this video, we shall be looking at another example of limits. In the last video, I told you the fact that we can compute and get the same exact limit if we took any other arbitrary point from which we compute the limit, as in we can take any direction with which we approach our limit. This time round, I'm going to try and show you a counter example to that problem. So we have example 2, for which we are given a function which is f of z, which is equals to z by z bar, as in a complex number divided by its complex conjugate. And we are asked to compute the limit of f of z, where z tends to 0. Now, spoiler alert, this limit doesn't actually exist. We shall look at the fact as to why it doesn't exist. Now, for it to exist, it can be found by letting the point z, which is x comma y, approach the origin, as in we're asked to approach the origin. We're asked to compute where z tends to 0, which is basically going towards the origin. Now we can go towards the origin in two ways, either via the x-axis, which is the real axis, or the y-axis, which is the imaginary axis. Now let's compute for these two separately. If they match, then the limit does exist, like in the case for real numbered limits in Math 110. I'm sure you guys have done a lot of these calculations where you have to compute right-handed limits and left-handed limits. And like in Math 110, where you saw if right-handed limits is equals to left-handed limits, your limit does exist. If in similar manner, if these two limits are equal to each other, that would mean that the limit does exist. Let's try and find that out, even though I gave you a spoiler already. Now, let's first compute going towards the origin via our real axis. Let us approach z, approach the origin from the real axis. Now, in the real axis, our complex number z is simply x comma 0, since on the real axis the imaginary part is basically 0. So to compute the limit, we have here limit z tends to 0, f of z, which is limit z tends to 0. Here we're approaching the limit z tends to 0 from the real axis. So our y is set to be 0. We can break down here the z by z bar to its Cartesian form, which is x plus iy divided by its complex conjugate, which is simply x minus iy. So as we've set y to be 0, we have our limit z tends to 0, where y is 0, both the y's in the numerator and the denominator are 0. So we have x plus 0 and x minus 0, for which we get simply 1, since the limit of z tends to 0 of, here we have since both of these are 0, we're simply left with x by x, and we can just cut both of these x's. We get here 1, and a limit here, the evaluation of the limit here, we're to evaluate 1, but 1 is not dependent on z, so we simply get 1. Now this is us trying to calculate the limit if we approach it from the real axis. Now let's do the other way around. Let's approach the limit let's approach the limit, which is the origin, from the imaginary axis, and let's see what happens. Approaching the limit, as in the origin, from the imaginary axis, let us approach the origin from the imaginary axis. We have our complex number z is equals to 0, y. Since if we approach it from the imaginary axis directly, as in y, x, if we approach it from here, there is no real part, it's simply imaginary. So our real part is equals to 0. And now in the same way we did it for approaching the origin via the real axis, we take the limit z tends to 0 for f of z, again breaking our function z by z bar to its Cartesian form, x plus iy divided by x minus iy. We have our x's to be predetermined to be 0, so we have limit of z tends to 0 of simply, if both these x's are 0, what we're left with are 0 plus iy divided by 0 minus iy, which is simply minus 1, because both of the numerator and the denominator, the x's in the numerator and the denominator are 0, so what we're left with in the numerator and denominator respectively are iy and minus iy, so we can cut the i's and the y's, giving us simply minus 1. Now minus 1 again here is not dependent on our z, so computing the limit where z tends to 0 of minus 1 is simply just minus 1. So as we can see, these two limits don't really match. These two limits give us different values, and since limits are unique, we must conclude the fact that these limits do not really exist. Thank you, and hope to see you again in the next video.